Hello, I'm Seema and welcome to part 11 of the chapter Chemical Bonding and Molecular Structure. In the previous videos, we have been discussing bond parameters and we were talking about the polarity of bonds. In the last video, I told you about the ionic character of covalent bonds, and now I will be telling you about the covalent character of ionic bonds. Just as no covalent bond is absolutely covalent, it has some ionic character to it. Similarly, no ionic bond is 100% ionic. It has some amount of covalent character to it. And you can measure this covalent character and you can identify the covalent character and you can understand what could be the reason of this covalent character. And this character was explained by a set of rules given by a scientist called Fajan. It's written, the spelling is Fajan, but it's pronounced as Fajan. We call them the Fakans Rules. But before I come to the Fakans Rules, let me just explain to you what is the cause of this covalent character in ionic bonds. We know a covalent bond is formed when two atoms which are deficient in electrons in their outermost shell, that is, which do not have their octet completed, they share a pair or more pairs of electrons, and this shared pair of electrons is known as a covalent bond. So they equally contribute one electron each, and this pair of electrons is shared by both, thereby decreasing or fulfilling that deficiency and making them acquire the octet. On the other hand, an ionic bond is formed when one atom, which has only one or two electrons or three electrons in its outermost shell, loses those electrons to acquire the octet of the previous noble gas and forms a cation, and another atom which gains those 1, 2 or 3 electrons to form an anion and acquire the configuration of the next noble gas. And now these two charged particles, that is the cation and the anion, they stay together due to Coulombic forces of attraction. Such a bond is known as an electrovalent bond. So when an electrovalent bond also has some covalent character, what is it that you expect in a covalent bond? A shared pair or electrons between the two atoms which are being shared by the two. So when is it that we see that a molecule that is ionic in nature starts showing covalent behavior? This is a cation and this is an anion. The negatively charged anion is usually bigger than the positively charged cation. And when the cation is very small, what happens as a result of a small cation? The nucleus is very close to the outermost shell. And a cation is formed by the loss of electrons. So when electrons are lost, the cation now has more protons, so the attraction of the nucleus is pretty strong, but an outermost shell is lost and the cation is smaller than the neutral atom. So this small cation, the electrons of the small cation, they experience a greater effective nuclear charge. Why? Because the number of the positive charge is greater than the negative charge, and the positively charged nucleus is like the magnet that attracts the electrons towards itself even more strongly, because the magnet is still strong and the nails, that is the electrons, have been pushed out of the outermost shell. So when you have such a cation which is small in size and whose effective nuclear charge is greater, it has a stronger attraction for electrons of the anion. Now the anion is usually bigger in size and the electrons are further away from the nucleus, and it already is negatively charged, which means that the number of protons in the nucleus is less than the number of electrons. So as it is, the effective nuclear charge per electron is less. And then there is a cation which has a stronger effective nuclear charge, which is in contact, which is close to it. So what will happen as a result of this? The positively charged cation will attract the negatively charged electrons which are just dangling in the outermost shell of the anion. And when this happens, you imagine the anion to be spherical, but this spherical anion now gets distorted, and the negatively charged electrons start pushing towards, are attracted towards the positively charged cation. And this distortion is known as polarizing, and it has polarized the anion. And when it polarizes the anion becomes distorted, and these electrons in the middle now, if you imagine the nucleus here of the anion is here and the nucleus of cation is here, these negatively charged electrons which are pushed towards the cation, they kind of start acting as if they belong to both the atoms. Because they actually belong to the anion, but the cation is also exerting some kind of a pull over there. So they impart, it is these electrons which are moving towards, which is causing the polarized anion, causes the molecule to act as a covalent molecule. So that is what imparts the covalent character to the ionic bond. Right? So this is basically what happens. Now, what's the difference between ionic bonds and covalent bonds in the physical properties? We see that the physical properties of ionic bonds or ionic compounds usually have high melting points and boiling points. They have a high solubility in water, they easily dissolve in water, and they have more thermal stability. The greater the ionic character, the greater will these properties be. And the greater the covalent character, obviously the lesser will these qualities be. So when you are in questions, when you are expected to compare the ionic or the covalent character, sometimes they trick you by asking you about these properties. Why is the melting point or boiling point of this higher and this lower? Why do you think this is more soluble in water and this is less soluble in water? Why is this more thermally stable while this particular compound simply decomposes on heating? So these are just trick questions which are actually questions about their ionic or covalent character. Now, a cation, how well can it polarize an anion is known as its polarizing power. How powerful is it to polarize an anion? And the ease with which an anion gets polarized is known as its polarizability. How easily does it get polarized? So that is the anion's polarizability, and the cation has a polarizing power. It polarizes the anion, and the anion, how easily it gets polarized, decides the greater the polarization, the more is the covalent character. The greater, which means the greater the distortion, the greater the electrons that come towards the cation, the greater would be the covalent character, because that much of sharing of electrons is taking place, and as a result, greater is the covalent character. So this is the basic, concept behind this. Now, what were Fajan's rules? How did he describe this polarizability and the polarizing power, and how did he relate them? But before we come to this, there is one more point that I'd like to discuss here. The ionic potential, the polarizing power, is calculated by the ionic potential. And ionic potential is given by this sign, that is phi. And ionic potential is equal to the charge over radius of the cation. We talk of the ionic potential of the cation mathematically. So from this, what do we understand? That the smaller the radius is in the denominator and the charge of the cation is in the numerator. So the covalent character would be greater when the charge on the ion is greater and when the size of the cation is smaller. The smaller the denominator, the greater the value of phi. So ionic potential, we would say, depends on charge and radius of the cation. So this polarizing power is calculated in terms of the ionic potential. Now we come to the Fakans rules. The numerical problems are not there in the syllabus, therefore just the knowledge of this is good enough to understand the concept of the Fakans rules. The rules are, the first Fakans rule is that the smaller the cation, the greater is the covalent character. How do we understand this conceptually? The smaller the size of the cation, the closer the electrons are to the nucleus, and the greater is the effective nuclear charge, and the greater the effective nuclear charge, the greater would be its polarizing power. Therefore, the smaller a cation is, the more, it is a small packet of greater attraction. So that's the smaller a cation, the greater would be its polarizing power, and therefore it would cause a greater polarizability in the anion, and as a result of that, there would be a greater covalent character. So if we take these elements, the chlorides of the alkali metals, that is lithium, sodium, potassium, rubidium, and cesium, if we compare the chlorides, the anion is the same in all of these. So what do we notice? Lithium is the smallest in size, sodium is bigger, potassium is bigger than that, rubidium and cesium are still bigger. The largest is cesium. So which one do you think would have the most covalent character? The one where the cation is the smallest. And where is the cation the smallest? Lithium. So lithium has the smallest cation, and therefore lithium is the most covalent in nature. Lithium chloride would be most covalent in nature, and cesium chloride would be most ionic in nature. The second rule, Fajan's rule, is that the larger the size of anion, the greater would be the covalent character. Now, how do we understand this conceptually? When we said that the cation, when it is smaller, the effective nuclear charge is greater. And the greater the effective nuclear charge, the greater is its tendency, is its polarizing power. On the other hand, if the anion is larger, the larger and larger an anion gets, the electrons are further and further away from the nucleus. And if they are further and further away from the nucleus, they are experiencing lesser and lesser attraction by the nucleus. And therefore, it is very easy for them to get polarized, for them to be attracted by the positive cation. So what do we notice? That the larger an anion is, the easier it is for its electrons to get distorted or to get attracted by the cation. And the larger it is, the more is its polarizability. The more is the ease for the anion to get polarized or to get distorted. So, what do we see if we take the different halides of lithium and we compare them? What would you expect? Lithium fluoride, chloride, bromide, and iodide. Iodine is largest in size and fluorine is the smallest halogen. Now, what would you expect? As the size increases, the anion iodine has electrons which are much away from the nucleus than fluorine. Fluorine has electrons in the second shell, chlorine third, fourth, fifth shell. So the electrons are so far away from the nucleus that these electrons, it would be the easiest to distort them, and this would get polarized easily, most easily. So we say the polarizability of iodine is the most, and therefore lithium iodide would show maximum covalent character. We now come to the third Fajan's rule. It says that higher the charge on the cation or anion, the greater would be the covalent character. The higher the charge on it, if the cation has more positive charge, then obviously the greater the positive charge, the greater the effective nuclear charge. Right? The greater the positive charge, it means it has lost those many electrons. If it has lost 1 electron, 2 electrons, 3 electrons. 3 electrons means it has got 3 extra protons in the nucleus. So the effective nuclear charge increases with increasing loss of electrons. Therefore, when you have the higher charge, it would have a greater attraction and therefore a greater polarizing power. So if you have, let us take the example of these three, the chlorides of sodium, calcium and aluminum. Sodium is 1 positive, calcium is 2 positive and aluminum is 3 positive. And if we compare these, although their sizes are kind of similar of the cations, yet we find that aluminum 3 positive has the highest polarizability. polarizing power. Why? Because it has 3 positive charges or 3 protons extra in the nucleus than the electrons, and therefore its effective nuclear charge is much stronger. It has a stronger attraction for electrons of the anion. And we keep the anion the same so that we can compare. The effect is only of the cation here. On the other hand, if you have the anion which has a larger charge, let us take an example here. Sodium, calcium, this question here. Mg3N2 and you have MgF2, right? So if you look at these 2 compounds, which one do you think would have a greater covalent character? Magnesium in MgN2, both the magnesiums in both the compounds have the charge 2 positive, but N2 has charge 3 negative, and this is 2 positive, and F2, that is F, has a charge of 1 negative. So fluorine is 1 negative while nitrogen is 3 negative. Which has a greater charge? Nitrogen. So which would, if it has 3 negative, it means that it has 3 electrons more than the number of protons that are there in the nucleus. So these 3 electrons are being stuffed into the atom, and after being stuffed into the atom, the attraction they feel from the nucleus as it is not enough, because they've been forced to enter where they did not have the same number of protons in the nucleus. These are 3 extra electrons. And when they have been stuffed, obviously, the 3 negative charge would have a greater chance of getting distorted towards the cation. Those electrons are as it is, the effective nuclear charge they are feeling is less, and therefore they would very easily get polarized. And that's the reason why Mg3N2, out of these 2 molecules, this one should be more covalent, right? Now let's come to the next Fajan's rule. The next rule says that electronic configuration of cations also decides how covalent a compound would be. You know, usually alkali metals and alkaline earth metals form cations, that is 1 positive and 2 positive. And when they form cations, they have the configuration of the previous noble gas. After losing the 1 or 2 electrons they have in their outermost shell, they acquire the configuration of the previous noble gas. But if you have transition metals and they lose these electrons and they form cations, they may have the configuration of the previous noble gas, but in the same shell, they may have electrons in the d orbitals too, because they are the transition metals. When they have electrons in the d orbitals, we know that the screening effect of d subshell is much lesser. The d orbitals are diffused. They're not very effective. The s orbitals are spherical. So they screen the effect of the nucleus and they shield the effect of the nucleus, and the electrons which are beyond that, they do not experience that much of attraction from the nucleus because of the strong shielding effect of s orbitals. The p orbitals are dumbbells, so they provide shielding only in one direction. If the p orbitals are present, they'll do it either in the along the x-axis, along the y-axis, or along the z-axis. But d orbitals are far more diffused. They are double dumbbells, and therefore they are even less effective in shielding the electrons from the attraction. So due to this diminished shielding effect of the d orbitals, the effective nuclear charge on the outermost electrons increases, because these d orbitals were not able to shield, and therefore the nucleus is more effective for the outermost electrons. So we find when you have such transition metals which are forming the cations, they have the d orbitals, and these d orbitals, they cause them to increase the effective nuclear charge, and if they have an increased nuclear charge, the effect is the same as that of a smaller cation. They have a stronger polarizing power. And if they have a stronger polarizing power, they would have more covalent character. So we find that alkali metals and alkaline earth metals, when they form ionic compounds, they have a stronger ionic character. But if you have a transition metal on the other hand, which has electrons in the d orbital, then you would have more covalent character. And you know, if you have 10 electrons in the d orbital and the configuration of the noble gas, such a configuration is known as a pseudo noble gas configuration. It is not actually the noble gas configuration, because you have the d orbitals. The noble gases have 8 electrons in their outermost shell. But if they have 18 electrons in their outermost shell, such a configuration is known as a pseudo noble gas configuration. So the reason is the same. The pseudo-noble gas configurations or transition metals which have electrons in the d orbital, they would have poor shielding effect, and hence the effective nuclear charge would be greater, and hence they would have greater covalent character. Now, having understood the basic Fakans rules, let us do these 3-4 more problems. We have beryllium chloride and barium chloride, and you're asked to compare the covalent character. Beryllium is smaller in size and barium is larger in size. And what does the first Fakans rule tell us? The smaller the cation, the greater the covalent character. Since beryllium is smaller, therefore the covalent character of beryllium chloride will be more than barium chloride. Then I told you about these properties, that the examiner is going to trick you with a question where he may ask you about these properties instead of directly asking you about the covalent or the ionic character. So if a question comes like, why is the melting point of calcium iodide more than that of less than that of calcium fluoride? Or the question may be like, how would you compare the melting points of these two compounds? Give reason why you choose this one to have a higher or lesser melting point. We know the more the ionic character, the greater would be the melting point. So we have to look at the Fakans rules, explain it according to covalent character, and then bring it to the melting point. Now, both of them have calcium. So calcium here, calcium. So that is not the factor that we have to compare. We have to compare the anions here, fluorine and iodine. Iodine, we know the larger the anion, the greater the covalent character. So iodine is larger in size, therefore this has greater covalent character. So we'll say, since this has greater covalent character, the melting point of calcium fluoride would be more. Calcium fluoride would have a higher melting point because it has greater ionic character. Then I just explained this one to you. We now come, why is barium hydroxide more soluble in water than magnesium hydroxide? Now he's asking you about solubility. Again, he's tricking you into believing that the question is about solutions or solubility, while actually he wants you to talk about the covalent and ionic character. The ionic compounds, they are more soluble in water. They very easily get dissolved in water. So why is barium hydroxide more soluble? It means barium hydroxide is actually more ionic in nature, and magnesium hydroxide is less. Both are hydroxides, and barium, and both have charge 2. Do you see Ba2 positive and Mg2 positive? So both of them have the same charges. You have to compare the cations. The cations, which one is smaller in size? Magnesium is smaller and barium is larger. Since magnesium is smaller, therefore it would have the smaller the cation, according to the Fakans first rule, the smaller the cation, the greater is its polarizing power, and therefore it has a greater covalent character, and due to which it is barium hydroxide which is has higher ionic character and therefore is more soluble in water. The fifth question is that you have to compare the thermal stabilities of sodium carbonate and calcium carbonate. The question could also be that one of these is thermally stable while the other one decomposes on heating. Which do you predict would decompose on heating and which one would not? So, or comment on the thermal stability of these two molecules or ionic compounds. So now we have to compare the ionic character or the covalent character of these two ionic compounds. And we notice that both of them have the same anion, the carbonate. So what are we supposed to compare? We are supposed to compare the sodium, that is the cations. Here, calcium has carbonate is 2 negative, so calcium would be 2 positive. Carbonate is 2 negative and you have Na2, which means that sodium is 1 positive. So what's the difference between the two cations? One has a 2 positive charge and one has a 1 positive charge. And according to Fajan's third rule here, you have that sodium, the higher the charge on the cation or anion, the greater is its covalent character. Since calcium has greater charge on it, therefore this has a larger covalent character. And if it has more covalent character, the one that has lesser covalent character actually has more ionic character. Therefore sodium carbonate would be thermally stable. And this will be unstable. Or you could say it gets decomposed on heating. I'd just like to come back to this once more to explain it because I did not explain this example. Now you have these two compounds, sodium chloride and cupric chloride, and you're expected to compare their covalent character. Sodium has the configuration of neon, or Na positive has the configuration of neon, and Cu positive has the configuration of Ar3d9. Now, due to the presence of this the electrons in the d orbital, which have poor shielding effect, the ion Cu positive, it has more effective nuclear charge, and therefore it has a higher polarizing power, due to which it causes greater polarization of chlorine or the chloride ion, and therefore this compound would be more covalent. So these were Fajan's rules and how to use them to explain the different properties of ionic and covalent compounds, and to explain the covalent character in ionic compounds. So with this, we come to an end to this subtopic. In the next video, I'll be telling you about the Vesper model. And if you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.